course, this lecture, and you will always receiving the lecture notes, lecture handwriting notes, and also recording. Okay, so I'm really thoughtful. Okay, I can give you everything I can have. Okay, so please make silent, silent, mute. Okay, good. Right. So welcome. I'm going to, yeah. You see, what I'm trying to do is I'm using 3 devices from Apple, and I try to make everything can be recorded and see online live, and you can see my handwriting and see me as well. So I did a really hard work on this and spent a lot of money to trial for a lot of apps or software. And now I think this is optimized arrangement. Okay, so this is my first time to giving this lecture in English. Okay, but don't worry about this, because if you cannot understand what I'm talking about, I have done an OCW in Chinese, and there will be 99% of the content similar to what I'm going to teach you or giving to you. Okay, so don't worry. So if you don't understand anything what I'm talking about, just click the OCW and you can make it 1.5 speed, and it will be really fast. And also there will be no joke, no personal sharing, so it will be time saving. Okay, but I guess this will be your good chance to how to say to correlate the English and Chinese version of the mechanics of materials. All right, so welcome. And I'm surprised that this is really interesting. Previous like 4 years ago, this course will have 100 people, 100 students. I don't know why. And then at some point it become 10. So I don't know. And then it comes 30. Okay. So I think it's I don't know, up and down. But before 5 years ago, this is my 10 years in MICU. Okay, so previous 5 years, they are all like 90 people, 90 students, 80, 100. So oh, it's amazing. And I need to change to other classroom, but I don't know why. But anyway, so I hope maybe it's because I record NYCU OCW, so reduce like 90% of the student. I don't know why, but now become English, so it becomes 3%. So I think it's worth to do a statistic experiment, okay, for this. So starting introduction. All right, so previously I only give 1 hour for the first day, but it's because I did that because I have 18 weeks, but now I only have 16 weeks. So which means that I don't have a lot of time to waste. Okay, so I need to, how to say 上好上满. I need to use an entire two hours. Okay, I'm sorry for that. This is because I cannot afford to waste time, because we only have 16 weeks. Okay, so here, mechanics of materials. Mechanics is something about force, okay, deformation or stress and strain, okay, in material, of materials, okay. So it kind of not related to chemical things. I'm really bad in chemistry. Okay, I'm sorry for that, but I'm looking to mechanics when I did my PhD degree. So mechanics. So my name is Nien-Ti Zhou Nien-Ti. Okay, my email is tslumenti@nycu.edu.tw. Okay. My office is in the third floor, 308 room. Textbook is here. Oh, sorry. It auto-correct. Here. Okay, here. Sorry. It auto-correct. I'm sorry. Here and good note. Okay, this textbook is a holy Bible in mechanics of materials. Even when I was your age, I was your age, I used these books as well. So this is kind of standard. Okay. Grading, classroom performance. Although I will never check the attendance, okay, but I sometimes, because I will have one Wednesday 9 a.m. Course, so I found that sometimes this will be really difficult for students to come, even for me, come here in time. Okay, so sometimes when I found, oh wow, 9 o'clock, only 3 or 5 students here, and I will give them special bonus because they are really on time. I'm really appreciate that. Sometimes I will be late as well. I'm sorry, but averagely, based on my experience, one semester, I may have 1 or 2 cannot get here in time because of the traffic jam or something. But yeah, I will try my best to not wasting all of your time. Okay. Right. So 10% is the class performance, and also if you point out what I have done incorrectly. For example, I write down like this. This is here, but I wrote it here, and then you point out, say, oh, professor, this is wrong, and I say, I appreciate your effort, and I will give you a bonus here. Okay, so class performance will be something from there, and right, and also maybe the introduction, but in the Facebook club, maybe I saw you, do a really good job of answering your friend's problem, answering your classmates' questions. It will be really nice of you if you can give a really thorough solutions, correct solutions. Okay, so based on the classroom performance, I mean introduction, interaction between each of all of us, between all of us. Then the quiz 1 and quiz 2 will be 15%, and midterm or final will be 30%. So this is basically how I grading in now. And then I would like to mention that please don't ask me. I mean, in the end of the semester, please don't email me or ask me if you want to adding an extra point. Okay, I really don't like that, because I don't like to refuse students, refuse anyone. So I really don't. I really hate that. So if you really want to adding extra point, please adding your effort. Okay, improving your effort beforehand. So don't make it in the end, and then you ask me, can I add in some points? Sorry, I cannot do that, because for the fair, okay, fairness, I cannot do that. If I adding for you, adding marks for you, I should adding marks for others. So please don't do that to me. Thank you very much. Okay. So, and also, maybe most of you can see the um, post from Facebook. Sorry, E3. And E3, you can have the link of the Facebook club. Please participate, join this club, and then you will see all the information from the club. And also, I will introduce our teaching assistant, Hong Liang. Hi, Hong Liang. Do you want to introduce yourself? It's okay. Well, he's my master student first year. Yeah. Good. Very good. Okay, very good, Pen. Very good, a man. Okay, good. Man or boy. Yeah. Anyway, good. Okay. So, Facebook Club. Oh, right. So if you have any questions, please ask him, and then if he cannot solve, then you can bring the question with me. Okay. So, yeah, and if you cannot solve it, you can ask Li Jun, our previous teaching assistant. Okay, both of them are really good. Okay, so I believe there won't be any problems that they cannot solve. But if they really cannot solve, I will do the final, defense, final try. Okay, so Facebook Club, please. This is syllabus. The first one is tension. So Hongliang, if you have any, did you leave the contact information of you to them? Contact information like email or email. Okay, so everyone can contact him via email. Okay, so anything else you want to say? No. So if there's nothing, you can leave. Or really? Okay. Oh wow. So see, he is really enthusiastic guy. That's really nice. But you don't need to waste time on this course because you took them. And yeah, I will ask you other things later. Okay. Thank you. So feel free to leave. Okay. Right. So syllabus. Chapter 1 will be tension and compression and shear. Okay. So this is the different loading style, loading types. The second one will be actual loaded member. Okay. Actually, is along a long axis. Okay. 轴向. Okay, actually loaded member. So this is a kind of when I'm adding tension or compression on this component, we should call this actually loaded members. And third one is torsion. Okay, shear forces, shear force, scissors. Okay, and bending moment, bending. Okay, and stress in beams is something on your in your ceiling. Okay, this is the beam. The beam support the floor. Okay, so you can stand on the floor, but the floor will go down, but the beams will support this floor and hold you up in our third floor or second floor. Okay, so beams are really important. But chapter 5 is only basic topics, because we have advanced beams in chapter 6, but it's too difficult, so we didn't mention that. We won't mention that. Chapter 7, analysis of stress and strain. Stress and strain. I believe you know that if you pass the introduction of material science and materials and material science, right? Stress and strain, and I will give you a more detailed definition for stress strain later. Okay, chapter 9, deflection of beams. I don't know if we have time for chapter 9, but I will try my best. Okay, if I don't have time, because now we only have 16 weeks, we may just stop here. But let's see. Okay. So, oh, by the way, if you have any questions, please just raise your hand. I will stop and then answer your questions. Okay. And also, students online, if you have questions, because I cannot see you, so maybe you can leave your message in chat room. Okay, and I will answer your question maybe during the break. Okay, so now let's talk about the missions of mechanics of materials. Okay, well, actually, I'm thinking, should I do the Chinese translation for each page? Because that's what I do in thermodynamics of solids. Which is the master and PhD students course. But because I don't have any OCW for that course, so I did translation each course. Each page. So I don't know if I should do that in mechanics of materials. Or maybe I can ask everyone if this page need to be translated. Okay, right. Okay, so until now, do I need to translate everything here? No. Do you need, if you need a translation, just raise your hand. So please translate it. Okay, so I will stop and then translate in 1.5 speed like YouTube. Blah 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 blah. Okay, let's go. Missions of mechanics of materials. So our goal, why we are going to study mechanics of materials, because we are going to study how safe of a material, safety, okay, and how can it works in engineering aspect, okay, serviceability, okay, how it works, okay, and stability, which means that it can always in the equilibrium state and maintaining its serviceability, right? So, for example, this is a bridge, right? This is not safe. It will become like that. Wow, terrible. It will, So basically, mechanics of materials need to be learned, need to be studied in Department of Materials, Material Science and Engineering, of course, and Civil Engineering and Mechanics of Engineering. Okay, Mechanics Engineering. So these are really important, really classic subjects in mechanics or material. Okay, so civil engineering, 土木系 need to be learned this, otherwise it will kill a lot of people. Really, you see. And luckily, because we are material science and engineering, so we only make some iPad or iPhone is in a really bad quality. Okay, so this is because we all care about the safe design. Okay, does the design of this material suitable for their applications? Okay, so how about stability? For example, this one. This is kind of a brass. This is a metal bar. The metal bar looks really strong, right? They have really strength, and also very tough. But if their shape is not good enough, like this, it's a really thin metal bar. So if you press that, it doesn't fracture. It just buckle. It's called buckle. Okay. Just it doesn't break. It just buckle, but still it's not stable. Okay, so still we are going to talk about safety, serviceability, and stability. Okay, so this is the purpose or mission of our course. Okay, no need to translation, right? Good. I believe students nowadays have better English level compared to the time I was. Okay, so I believe everyone can understand what I'm talking about. Then, because this is a bachelor course, right? So which means that this is not too advanced. So this is kind of the first course, or not first course. I mean entrance course for mechanics. So we have a really basic assumption to make things simple. Okay, so basic assumption is that we study objects are solid and deformable. What is not something we treat that as undeformable? Water. Water cannot be deformed, right? If you press that, it just go away. Okay, but something like I mean everything here, yeah, is deformable. Although you press that, you didn't see anything deformed, but actually it deformed. Okay, slightly, okay, slightly. Okay, so we assume that everything is just like this. Is with this object has four assumption. They are continuity. They're continuous, right? Does it continuous? No. So we are not talking about this. Form. No, we're not talking about this. Uniformity. They are all uniform. Simple. Are they uniform? No, of course, they have some gap, right? So they are not uniform. Isotropic. The direction in the material are all the same. So if you rotate that, the material property won't change. But you see here and here, you see here, if you this kind of doing this, right? So if you rotate that, if you loading in the same direction, the property will change because the orientation of the material changed. So this is not isotropic. Okay, but this one is isotropic. This one is not isotropic. Of course, polycrystalline, they are all has different orientation in each grain. So they are not isotropic. And also this is really important things, infinitesimally deformed, small, really, really small deformation. For example, this one is the arrow, right? Arch, I don't know, the arrows. You have a really big bending on this. We're not talking about this because this is really difficult to calculate. Okay, we only talk about something like this. If we press it, it will slightly deformed, just slightly. Even our eyes cannot see that. Okay, so we only talk about this basic, the object with these four basic assumptions. Okay, do I need to translate this page? Good. So let's, after you saw the syllabus, I believe you found that four component, different loading type, right? Tension, compression, bending, shearing. Torsion and shearing is a little bit similar, but we will talk about this later. But these loading type, tension, shear, something like that, they actually corresponding to four components, four types of material in different shape. Okay, the first one is link. It's just a bar. Okay, just a bar. So this is a bar. Okay, and so if this link, the link can be loaded by axial force along its direction, you can uh, compress it and make it tensile, apply tensile stress, tensile loading to stretch it, elongate it. Okay, elongate it. Okay, so there's a link for axial force, axial force. Or if you have shaft, you can imagine that the shaft is kind of rotation for the wheels in cars. Okay, so if you have a tires around this bar, and you have to rotate the shaft. Okay, so the rotation and the interaction between the rotation, the shaft and the tire will be the torque, 扭转、扭曲、扭啦哦 torque. So you can imagine that. Sorry, I will plot something. Good. Right. So you can see that here. the torque has a blue and double arrow symbol. Okay, the torque, you can imagine that it is with your right hand, with your thumb, along that double arrow, blue double arrows, and then with the four fingers rotate. So you can imagine that this Tx is a torque along the x-axis and rotate like this. So imagine that you can rotate. So this symbol is equilibrium to rotating this shaft, this shaft like that. But I won't make this arrow stay because this one equal to that one. So I cannot double plot. Okay, so I hope you can understand what I'm talking about. So if I don't use this, I can use here. But because I using this, I cannot make it double application, right? So I still need to remove that. The my and nz is kind of moment. Moment is also a kind of so you can imagine that the torque, the blue double arrows are all the force with the force force arm with the distance. Okay, so force with the distance, so which means that you can rotate something like the 好难解释哦，杠杆，我不知道怎么不会讲，总之就是杠杆啊。So the torque means that you have force and the 力背要怎么讲 ？Force arm, distance. Anyway, you will know that. Okay, I will give you more detail later. So moment and torque are actually similar. So you have the force and the distance between the objects, so you can make it rotate. Okay, moment and torque are all similar. And the other is shear. Okay, shear is a kind of something like that. Okay, or that. Okay, so with a different direction. Okay, so this is a shear. So beam and column. Beam is something like that. You can see that. And column is this one. All right, so they support the floor, and maybe the column should be compression during compression or tension when you facing encounter earthquake. The building is kind of shaking, so which means sometimes this column may be pulled along toward the top, and the other will compress. So when you do the shaking, so we are talking about 4 components. This 4 in our class. Okay, so and of course this one will be the easiest one. Okay, so it will be the first chapter and second chapter. Okay, do I need translate in this? I mean, sometimes I translate in this during our course. All right, can I continue? Good, thank you very much. So now let's talk about chapter 1, tension, compression, and shear. Most of the content has been learned in introduction of material science and engineering. Okay, so 才到. Okay, so I believe it will be really fast. So introduction to mechanics of materials. Right. So again, we are talking about safety design. Safe design. We want to study the structure or single component. You have single component, and if you have many components, you will have the structures. Okay, the structures. After, of course, you need to give it some loads. Okay, put some weights or give some force. It will result in stress, strain, displacement. Okay, And then if it exceeds certain values, it will failure. Okay, but we don't want to talk about this in our course. We only say, in this course, we only say, okay, please don't cross this line. We will have allowable stress, allowable strain. So please don't cross that line into this area. Okay, so we're just going to do that. Again, if you want me to translate that, just let me know. Now, starting to write down something. Okay, so now we're going to review something you have learned in your senior high school, maybe physics. When you do the simple mechanics, which is statics, 静力学, okay, statics. I believe you have done some force balance, right? Moment balance, right? So when you do that, you typically write down some arrows. Okay, so now I'm going to set the convention of these symbols. Convention, 符号的规则 ，OK， 符号的规则 ，OK。So now, sometimes we have a force acting on point B, and so we will call it FB, force at point B, okay, and or we will have distributed load. What is distributed load? Which means that the loading is acting. Ooh. Load is acting on a unit length. I mean, on the section of the length. Okay, so this is called Q1. Q1 is called a code distributed load, 分布载重 okay, and it has a really, this is important, the unit is N Newton per meter. So you can see that distributed load is not a load. It's a load divided by meters. Okay, so Q1, the Q1 has a unit N divided by M. Okay, the unit is N divided by M. Of course, we are talking about MKS unit system. MKS 制啦. Okay, right. So this is distributed load. But when we are going to do the force balance of this entire system, this distributed load is really difficult for us to do the force balance. So we are going to use resultant force. The resultant force is actually equilibrium to something you are going to merge. So Q1 is something need to be merged. So here, I will do this. It's called FQ2. The FQ2 is the resultant force of Q1. Okay. Well, you can say FQ1. It's okay. Just saying that the total effect of the Q1 distributed load is equal to FQ2. Okay, and FQ2 will will penetrate the centroid of this area. Okay, in the middle point of this area. Okay, so here equal to Q1. Equal to Q1 times L. Oh, the L is the length. Okay, so you see distributed load Q1 times length L. So the unit become N is Newton. So FQ2 is Newton. Of course, this is the force, right? So when you do the force balance equation, FQ1, FQ2, X force balance, Y force balance, we typically make the distributed load into the resultant force. Okay, we don't use this Q1. It's a shape. No. We use the F2. I mean FQ2, resultant force with a dash arrow. Okay, and then we don't need to consider this. And now we use this to represent this one. Okay, when we do the force balance. Okay. If you can understand this one, I will continue for the reaction force. Reaction force is that if this system is constrained by something. For example, this is a pin, 大头钉, pins here, it fixed there, but this is a pin, right? This is a pin. So this is a pin. Imagine that if you have a bar pin on the wall, okay? Can it move up? No. Can it move to left or right? No. But can it rotate? Yes, right? So which means that this pin can make it not going to right hand side, X, and cannot go to Y direction. Sorry, this AY. Ugly, sorry. How can I make it AY? Okay. So AX and AY are the reaction force provided by the pin here, okay? The pin here. So which means that it can, I mean, this one, the force FB and FQ2 maybe have some force, resultant force, but A will still be there. So the AX and AY actually are unknown number. Usually the reaction force will be our unknown number. And this Q1 or FQ2 or FB will be the known number because there's people to apply that. Of course, people know the value. But the reaction force, we don't know yet. We need to do the force balance equation to solve this AX and AY as the unknowns. Okay, so with the dash, slash, arrow with slash, it means that reaction force. Right, and then if you can apply something on the bar with the rotation, if you have the hand to rotate it, you can also apply MA. It's a moment, so you can rotate this bar. Okay, so the symbol will be drawn like that with a half circle with the arrows. Right, so this is this is the how to say, the symbol convention of symbol for the mechanics of materials. OK， 这个需要翻译吗？总之就是符号了啊，符号怎么画啊？那我觉得这边比较重要就是反作用力，比较需要大家去思考一下。反作用力的这个值啊，会随着外力而变化，所以我们还不知道它是多少。哦，那是通常都是未知数，因为你加的力才是你人是加的嘛，所以你知道它自己是多少，所以你必须要靠力平衡的这种公式去计算，就方程式啊，去计算出 ax ay 这种东西。Okay, so that's it. Now let's talk about normal stress. The normal stress, the definition of a stress. Okay, stress is really important. I guess you have learned this in the introduction of material science and engineering, but I will give you more detail. Okay, stress. Please, after you pass this course, please don't say anything about stress balance. This is incorrect. There will be no stress balance. We only have force balance. Okay? Stress is something, some magnitude, some values inside the materials body. Okay, inside materials. So I believe you have heard someone said, your friend maybe, your friend said, oh, I'm so stressed, which means that I my mental has some stress, have some bad thing happen. Okay, but when you talk about pressure, the pressure is kind of outside, right? Air pressure. Okay, so pressure and stress, they are different, although they will have the same units. I will talk about this later. Okay, so now stress will always inside the material's body or surface. Okay, but only on the materials, only in the material. Okay, the normal stress definition is when you have a prismatic bar. What is prismatic bar? Prismatic means that equal area throughout the object. Okay, equal area throughout the objects. Okay, so if you have something like this one, is that prismatic? No, it's not prismatic, but it is prismatic in this section. This is prismatic in that section. Okay, but entire total in generally in overview, this is not the one I draw is not a prismatic bar. Okay, so a prismatic bar is that. So if I give you these things, and then it will has we take a look. We will take a look. We cut it imaginary. Okay, we cut it. Take this here. Okay, and then if we have a pressure in from outside. Okay, well, I need to be really precise. In the middle, in the center of the prismatic bar, and it's called P. Okay, if you have a P in the on the surface area, and then we do the loading. Okay, so suppose that section will become longer, right? So this one become that one. Okay, so L become L plus delta. Okay, and you can imagine that this area also has pressure. Sorry, load P. Okay, this section always the material will transfer the force, pass. The force will flow through the material. So even this section is not the one is subject to the outer loading. It still have the force P acting on it. So the P will make the L become L plus delta. Okay, and because this section is in the middle of the bar, so the P force will make it a uniform load. So you can imagine uniform distributed load. Okay, so here I would like to draw down. So this is the distributed load and equals, and the resultant force will be P. Okay, so the P on this surface, M surface in the cross section, it will be P resultant force P, but actually it's a uniformly distributed load. Okay, so now we will have 10 minutes break, and I will see you after 10 minutes. If you have any questions, just come to here. See you later.
就是那个，我大阪大学那个完全不说，我大阪大学都完全都输入，就是数学真的也准。然后现在就是要申请奖学金
OK，
然后申请奖学金，然后再配合老师写的推荐，
没问题。
然后我们等下把那个推荐信的格式重要。好，非常谢谢。
要英文还是中文？
中文就会，因为是台湾的奖。
好，太好。
然后我大概了解我考生的那个项目先做完，就是看那个 supplementary material。然后就是以后我再跟您报告这样。
对，
然后用回去，然后谢谢。
这样。
我是自贡系，在我空气中，你去写程序，
是的，
系统相关的课程。
材料系比较没有，土木系比较有。
这土木系的东西。
应该说力学都是同一个东西啦。那我们材料系可能就学到材料力学，大概就结束了。但实际上要做模拟计算、材料计算，其实 continuous materials 其实mechanics 还蛮重要的。continuous 其实就是弹性力学。你可以不是啊，应该说土木系有一门课叫弹性力学，跟 continuous mechanics 是非常贴近的。continuous 其实就是连续体的力学，那弹性力学只是这里的一部分，还有塑性力学，塑性力学也是弹性力学，不讲错了，连续体的，对，所以等于是说，它是一个大的力学的分支，对，然后弹性学就是在细的分支，
所以这堂课我也教到这种东西。
你要先学这个，再学这个。
不然这是更进阶，
这是更进阶，超进阶的。你会发现叫什么叫什么 tensor， 你有听过 tensor 吗？
有。
对，那这个就是其中一个 component。你等下我们之后就会介绍，接下来就是后面就会介绍了。反正这个东西就是啊，这个。 这种东西，应力的元素就是什么面都是就 continuous material，mechanics。哎，
对，可以这个算是就是他们算是比较基础嘛，不要修这个东西前，
这个以后再修
对修的，但是这个要到多去修这样。
我觉得是
哦，了解，
机械系可能也会有，
也是
可能
哦，了解，好这样子。
对。请问英文听得懂吗？好，谢谢。对。
因为我们实际上是一个这样子转，一个是这样子的，你这边都是什么？这样子说这边嘛，因为一个是这样子转，所以它比较小这里。大概就这是摆一个。
Wait. Welcome back. So last hour, is that everything okay? Everything okay for you? So my English is understandable, hopefully, right? Okay. So if you cannot understand my English, just raise your hand and let me know. Okay. Or you can email me. Right. All right. Okay. So what I'm going to talk about is the definition of this normal stress. Okay, I believe in the introduction of material science and engineering may not have such detailed explanation for the stress, because this is the most important thing in mechanics of material, this course. So I need to give the really clear definition for that. Okay, so you can see next page. This is finite element simulation. Okay, you can imagine that this finite element simulation is cutting every pieces of this component with the small element like this. Okay, and the computer will calculate each of them and then sum it up together. Okay, so our human hands cannot calculate such many elements at one time. So we need to use computer. Okay, so imagine that this bar is this bar. Okay, and you have a center point load. The load applied on a point. Okay, so you can imagine that actually, if I draw it exaggeratedly, it will look like that. It will look like that. Okay. If I draw it exaggeratedly, 就是夸张的话, it should be looks like that. So it's just like if you squeeze your skin, it really hurt, right? Okay, and so you can imagine that the stress in this place, they're very, very complicated because the shape is changing, right? So the stress here are very, very difficult to calculate by your hand, okay? So it will be difficult for us to define the stress by using the elements here. But so you can imagine that the force like a water, like a river, okay? It will something like it will flow like this. Okay, kind of symmetry. So if the segment we'll talk about is in the middle, you can see the color here, the color, they are the represent the magnitude of the stress value. Okay, stress value. So you can see here has a really higher, relatively warmer color, which means that they have higher, greater stress value. So here you see the same color, really uniform. Okay, so when we talk about the stress definition, it will be easier for us to use this section to calculate the stress. Of course, every element can be calculated. The stress of every element can be calculated. But if we talk about the definition of normal stress, it will be easier for us to take this section, which is far away from the actual applying load application points, because this place will be really complicated. The stress distribution will be really complicated. You see here, if I cut it half, you see this is maximum, like, but after that, it will become a uniformly distributed stress. So that's the reason why I will plot this, because in that section, the force is flow like a uniform river. Okay, it's a calm, stable river flow through the materials. So that's the reason why we choose this section to define the stress. But also you can see that because this is the point load, make it like that, right? So you can imagine, you can see that they are all blue because they just escaped from the force flow, right? So this blue part is actually stress free, stress equal to 0. This is really interesting. How can I wrote it? This is stress free. Sigma x maybe equal to 0. So the dark blue part, okay, so because they are escaped it, because this place cannot sense the force P, okay, but after the flow of the force, they can sense. So you can see that this is kind of something like that, right? So this blue, dark blue H is stress free. This is really interesting. Okay, so if we talk about the stress, this definition, we cannot take this region for the teaching class because this is really complicated. We will choose this one. Okay, so that's the reason why we choose the middle part of the bar. 这个可能要讲一下。总之啦，就是那个力呀，是点力，做在一个点上的话，它好像是一个这样捏你的皮一样，这样子像一个山缝一样弄起来。那这样子旁边的地方啊，它其实那些旁边的这些点，它其实没有感受到力的，它看不到力啊，力就是这样子就通过去啊，根本没有流到它这边，所以它其实这边周围这个圆圈圈的周围其实是深蓝色的，是完全没有力的。但是如果是中间，当然是红色力，哇，超大的 stress， 超大的应力。那所以说拿这一个地方来给大家定义应力，那就太难了。所以我们课本上讲的话都是讲中间这个，因为它是很均匀的流过去，这些力就像是一个分布载重一样，然后这个分布载重作用在这个解密机上，就好像是一个 resultant force P 一样的力。那这样的话，这边定义起来就比较好定义。OK， 好，大概是这样。So if you can accept what I've talked about, we do the normal stress definition. It will be sigma. Sigma is the sigma. Yeah, I should give you sigma. Okay, how it pronounced. Sigma is a stress symbol equal to P is the loading actual load value divided by cross section area A. Okay, for cross section area A. You can imagine that the force is uniformly distributing on this surface. Okay, so this surface take the entire P. So each point on this area has the value, the stress, sigma equal to P divided by A. Okay, so the units will be N divided by M squared. M divided by N squared is Pascal. PA is also the same, has the same units with pressure. But again, I mentioned that pressure is outer surface things, air pressure, wings pressure. But our stress is inside our body, inside the material body. So they are completely different. Then I'm going to talk about the convention of the stress. Convention of stress is tensile stress. Tensile stress is positive. Compressive stress is negative. There's no reason for that, just convention, just the rule, okay? And uniform stress is assumed. You see, uniform stress. So we are not talking about this part. We only talk about here, okay? So you can imagine that we talk about a material bar and we kind of neglect this region. We only talk about the most of the region with the uniformly distributed load. Okay, so uniform stress is assumed. And force P needs to be applied at the centroid of the core section. Yeah, you can see that. If your load is applied on here, oh, it will be really difficult to, the loading may not uniform anymore, right? So the load may has something like that. And then the value may not be the same, right? Here is symmetry, it's okay. But here may not be the same. So sigma equal to P divided by A, this one is not uniform anymore. Okay, so force P is need to be assumed at the center. If you do that, we won't discuss this. Okay, we won't discuss this. Okay, we won't discuss this case. Understandable? Yeah. Do I need to translate this? Okay, good. Next one, normal strain. Corresponding to normal stress, normal strain is a result. Okay, I mean stress and strain, they are all result of the P here. Again, a prismatic bar with the cross-section area, the same thing. And after the loading, we have PP here, P, and it becomes L plus delta. The delta is the increase in length. The L is the original length of the segment you picked. Okay. So the strain definition will be the epsilon. The symbol will be epsilon. Epsilon, and this is called delta. Okay, divide by L. Delta divided by L. Okay, no units. Oh, no units. Very important. No units, because delta is m meter, L is meter as well. So meter divided by meter, no unit. So sometimes we will use percentage or the value. Okay, so sometimes you can use percentage, or you can, for example, 0.00, sorry, 0.2 equal to 2%. Okay, this is example. E.g., okay, here's an example. 0.02, if you have a strain equal to 0.02, you can also write it as 2%, right? That's it. Sign convention, again, tensile strength equal to is a positive, compressive is strength is negative. We also assume that they are all homogeneous, okay? The material is the same everywhere in the bar, okay? Yeah, that's it. Right, so if you can understand this, we can have a quick, simple example. Very simple. Pressure P. And if you given that P equal to 2kN, and diameter will be the will be the D equal to 50 mm. So we were going to use MKS unit, okay, system. And then we can have sigma equal to, and please determine the stress in the bar. Okay, so P divided by A, P divided by pi D square divided by 4. And it will be 27 times 100, sorry, 1000 Newton, because it's Kn, and it's pi 0.05. Okay, so MKS unit system equal to 13.8 times 10 to 6 ha equal to 113.8 m ha. M is 10 to 6. I believe all of you know that, right? So normally mechanics of materials. In this course, our material stress value is more or less m pa, g pa. So if you count like pa, it's too small. Okay, so when you do the calculation and then you find that the value is too small, maybe you have something wrong in the unit, right? And the bar has original length L equal to 2.0 m, and subject to the load intention, the elongation by 1.4 millimeter. Okay, so please determine the strength. So easy, right? Well, it's just a warm up. And I believe some of you heard that from your seniors. Let's say mechanics of material is one of the most difficult courses in this department. I don't know, maybe I agree with that. So if you can get a really good marking in this course, which means that you are good. Let's do some challenge. Okay, see, epsilon equal to 0.0007, which means 0.07%. So you can see that the elongation is really small, right? Infinitesimally small deformation. Very small. Okay, so that's it. So basically, that's how I give the course. Okay. Yeah, this is the best I can do. Okay, I can support. I can give you the material of the blank notes and also handwriting notes and recording. Yeah, that's what I can offer to you. Interesting. In the first few years of my professorship, become a professor, I felt really difficult to speak in English in the course. After 10 years practicing, I feel okay. Although some of the terms, I still have some difficulty for translating that, like 杠杆, like, or especially when I telling the joke or sharing a story, personal stories. I found that it was really, really funny if I do the translation. I don't know why, but if I have mood, I will share some joke or some. If I have mood, sorry. Right, next one. 那天总刚刚讲什么？我说啊，就是10年前我在开 EMI 的时候，我就觉得哦，好压力哦。但是现在我觉得还好啦，随便啦哈，可能已经老了，就是算了啦，脸皮比较厚。然后我终究还是常常会发现一些奇怪的字，就是正常，有些字就是转不过来，就是无法用英文。那有的时候我在讲笑话，或者讲我自己就是一些我觉得值得分享的事情的时候，要翻译成英文，其实还蛮好笑的，就是本身没有那么好笑，但是翻译成英文就会很好笑，这种感觉。那我也不知道为什么。好，那只要我有心情，我就可以跟大家分享一下未来一些有趣的事情。我对人生最近有很多体认哦，就是例如说，就是说命定论。你看命定论怎么翻译？怎么办？命定论啊，就是一切的事情都是必然的。好，这就是我42年来的经验告诉我，就是一切都是必然的。So let's translate in English. That's really difficult, right? Recently, I found that I faced some difficulties in my life, and I start to reading a lot of books, and I made a conclusion that everything is destiny. Everything is fixed. Yes, everything's fixed. Because all the decision is all the decision made is according to the chemical status of your brain. Okay, so you thought this is your free will. Your thought. If you thought you decide that you decide to buy this clothes, you decide to buy these shoes. No. Your chemical of brain decide that. So your chemical status of your brain actually is a function of time. So you're born, and you're destined to have to eating some certain food, and then your status will, remain fixed. So everything is fixed. Yeah. Or if you say, I want to make some effort from now on, I want to study hard. That's because your mind, your chemical of the brain asks you to do that. And then you thought that this is your free will. Okay, so this is my negative thought, but I believe this is true. Okay, 听懂我在讲什么吗？就是你的所有的决定其实都是你当下的化学的状态，脑袋的化学状态决定的。然后那个有没有自由意志呢？我们以为那是自由意志，但其实不是，其实你自己选，就是脑袋帮你选这样。所以你当下觉得说，哦，我要用功，我现在开始努力用功，那是因为你现在的脑袋状态这样，然后用功，而不是说，就是你自由的选择说我要用功这样。好，总之啊，我觉得这样我有点太消极了，常不能对二十几岁的人这样讲，但是大概就是这样。好，没有，这只是分享一下而已。Anyway, let's continue our lecture. You cannot hear that in OCW, right? So given P equal to 240 kN, okay, there's a tube. There's a tube. What is tube? 管子. Tube. This is empty. Okay. There's only this is the cross section. Okay, and there's a light plate, the blue plate on the top, and then you press the force on the center of the light plate, and then the material tube will be the length of that is L. The outer diameter will be D2 equal to 130 mm, D1 is 90 mm, length is 1 m, and shorten of the length delta equal to 0.55 mm. Okay, so I want going to see calculate the compressive stress sigma of this. Okay, we are not talking about this. Okay, we're talking about that, because this one you have the really point load at the center, and it will be really complicated in the blue material. So we are not talking about that. We talk about this gray material. Okay, and also strength. So now, you can imagine that the gray stuff will come will have the distributed load on this area. Okay, of course the sum of this arrow will be P. Okay, and the area will be A. So the A here, so the first problem, A equal to pi divided by 4 D22 minus D12 equal to pi 4 132 minus 92. Oh, sorry, 90 square, not 2. 6912 mm square, but we're using MKS unit. 6912 minus 10 to minus 6 m square, and sigma equal to P divided by A, 240000 divided by 6912 times 10 minus 6. And because this is compressive, right? Minus, this is m squared, okay? Equal to minus 34.7 m. Okay, so this is the stress, compressive stress in the gray material, okay? So suppose the stress here is more or less minus 34.7 MPa. But yeah, something like that. Yeah. So because this is uniform, right? You're using this blue shade, blue black plate, apply that. So kind of uniform. Right. So this is the first problem. The second problem. Epsilon equal to delta divided by L. So 0.55 millimeter divided by 1,000 minus and 5.5 times 10 to minus 4. Okay, feel free to make it percentage, but it's okay. I mean, as long as the value is the same, you are okay. You are good to write it down like this. Epsilon equal to minus 5.5 times 10 to minus 4. Very small value. I also found that I don't know, should I share such negative things? You know, 10 years ago, I was really positive man, very positive. And after 10 years, I become a negative person. Anyway. All right. Do I need to translate that? Okay, good. Next one. This things is a rod hanging a weight, and fixed on a ceiling. Okay, and the circular steel rod, this one. Okay, length L, diameter D, bucket weight is W. Okay, and then find sigma mix. Oh, account the weight of the rod itself. Rod densities gamma. Oh, so we need to consider the self weight of the rod. So imagine that. Do you want to answer the questions? I'm going to ask questions. So where is the sigma mix occurred? Where does the sigma mix occurred in this rod? Which point? Here. Which one? Do you have? Okay, sorry. Wait, you. Sorry. The top. Why? Okay, you are right. So do you want to say the reason? Yeah. You are right, but do you want to speak English? EMI. You want to try it? Yes. The whole weight, right? Whole weight that will act on that point, right? Very good. Your English is really good. Wow. So good. Both of you are good. So please tell me your number. You want to speak English? 110. 13039. Good. Sorry? 6. Is that correct now? Good, thank you. How about you? 1. Sorry, again. 613. 27. Good, good. Okay, that's really good. So I think this is a good opportunity for you to talk about the value. Okay. Sorry, the numbers. So for example, maybe you can learn like 111. Okay, or you can say 111. Right? And 613. Sometimes in British, because I study in UK, British will say 027. So maybe 111, 613, 027. Okay, so sometimes you will say that. Otherwise, you will say 027. This will be because you know British are quite lazy. Okay, so there was a 027. Okay, just for your information, for your interest, it's not important. I just share something that OCW won't share with you. Okay, so good. Maximum sigma max will occur in the top of the rod. So now I will give you a really important concept now. The concept is that if you want to see the stress at any point, just cut it through it. Okay, just cut it. If you want to see any points, you just cut it and divide them into 2. Okay, so this is a really important concept. So that's what I'm going to do. It's called drawing free body diagram. Okay, so I want to see that point, the sigma at that point. I know that sigma will be the mix. Okay, so I will just cut this point. I will cut this point and divide this system into 2. So can imagine that a very little tiny there, and divide, separate them. Well, okay lah. Okay, and it should be W, right? And I just cut it, okay, and separate them. And you can imagine that there will be load here, 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 because they were considering the self weight, right? And what should we do about this? You can imagine that everything, every point in the system are all in equilibrium, are all stable. Okay, so if we cut them and separate them, you can imagine that each part will stay equilibrium, will remain equilibrium. Okay, so when you cut it, if you only see this part, it must be something, some force here. If not, if there's no force here, you can imagine that everything is stone wall. So this part should be fly away, right? So it must has some force on the top. Okay, and after you cut it, you must have another things with opposite direction but the same value in the opposite cross section where you cut it. Okay, so here will be F max. And why you cannot see this F max here Because there's internal force. When you stick them together back, they will cancel each other and you won't see here in the whole system. Okay? So you can imagine that you are the really good surgeon. You cut it and analyze it and put it back and nothing happened. Okay? So you can imagine that. So the F max is the point that you are going to see. I mean, the point you want to see the stress because you want to see, before you calculate the stress maxima, you need to find the F maxima on that point. So I will just cut it and do the force balance in this diagram. We call free body diagram. Okay, because everything looks like free and they are all remain there and every part are in equilibrium. Every part is in equilibrium. Okay, I hope you can understand what I'm talking about. So sigma max will be F max equal to W plus W0. The W0, okay. I use different color. W0. Okay, of course, this is self weight. Okay, and it's called W plus G is the gravity, gamma is the density, A is the area, AL will be the volume. Volume times density times gravity will be the weight, equal to W plus gamma pi d square divided by 4Lg. So the sigma max equal to F max divided by A equal to W A plus gamma Lg equal to 4W divided by pi d squared plus gamma Lg. Okay, that's it. Sigma max equal to that. Understandable? Okay, so this problem is actually not a big deal, but the most important part, key things I want to deliver to you in this problem is wherever you want to see the stress, you just cut that point and divide them into two. And then to balance one of the part. You can balance here or you can balance there. Okay. Today I demonstrate that I choose this part to do the balance, but you can also balance the upper part. Maybe you can go home and try by yourself. Okay. And how to do that? Because you can imagine that there's a force, right? And this is W, right? And you have a fixed point. So you actually has a reaction force, reaction 反力, supported by that point. And of course, here is a reaction force. And this reaction force will equal to F max. Okay, so you need to calculate what is the reaction force. And you will find that the reaction force actually become this one. Okay, so I will encouraging you, go back home, choose upper part, and do the force equilibrium again, and you will get exactly the same value of F max. Yeah， 这样听得懂吗？最重要的东西，在这个很简单，但是最重要的这一题的重点在于，以后你要看哪一点的应力，就切哪一点。一切完以后把它分开，分开完以后就会有就是上面或下面或左边跟右边，然后随便就两部分，你爱选哪一边都可以哦，都可以。 那我今天是选下面的，你可以回家试试看上面的。那下面呢？哦，我选下面的话，反正一切完以后，一定会有个力出现。如果你没有这个力，你没有这个 F max 的话，你只有这个桃红色跟红色，那下面这个早就飞走了，就往下飞走了。不对啊，它还留在那里啦。所以表示说你切的地方一定有个力去 balance 平衡下面的东西。好，所以这个 F max 就这样出来，就可以画出来了，就可以算出它 F max 多少，然后就可以用它来算 sigma max。好，这就是这个自由体图 （free body diagram） 这个很重要的概念。Okay, so why strain and stress? Why it's not just using displacement and the force? Okay, because the strain and stress are related to materials itself, and load and displacement are related to materials and geometry. Okay, geometry will taking the effect on the displacement and force. Okay, so because we are material science and engineering department, so we are focusing on material itself. Let's demonstrate in these tests. So the Galileo, who is the greatest scientist and engineering, ancient scientist engineering, he found that when he do the tensile test with 5 samples, and the first one, ABC, steel, and the DE will be aluminum, okay, and with different shape, okay, and they do the tensile test, and they found 5 different curves with displacement and load for the x and y axis. They find 5 different lines, and then he found that if they use percentage of the elongation, which is strength, right, and they do stress divided by their cross-section area, they become 2 lines only, and each line represent steel and aluminum, which means that if you plot this line, you eliminating the shape effect. So you only see the material properties. Okay, so strain and stress are more important for us, for materials scientists and engineers. Okay, engineers. And how to measure the stress and strain curve? We're typically using standard ASTM standard, American something, American standard, blah 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 blah. Okay, why we follow American? Because they are the most powerful country in the world, so we will follow them. Okay, so one of major standard is ASTM. So we typically focus on static test. We apply load slowly, and we try to make every step stable in equilibrium. Okay, so not okay. Yeah, so as you know, when you do the quick load, the thing may break more easier, right? Especially when you go to bathroom and you use the toilet paper, and you apply your load slowly, you can have longer paper, right? But it just break, right? So you can see that material has different behavior if you do the loading quick or stable, right? So static tests and dynamic tests are 2 different things. And also dynamic tests sometimes will including the cyclic loading, unloading, loading, unloading, loading, unloading. We can test their fatigue. Okay, yeah. So you can we have more complicated properties measured by dynamic tests. Okay, so of course, in our mechanics of materials, we only focus on static test. Okay, and usually I will have two machine picture, but sorry, I don't know why they missed. Yeah, I hope I can. Yeah, but you can find that on the internet. That's okay. Okay, right. So I will see you tomorrow, 9 a.m. and continue our lecture. If you have any questions, just let me know. And that's it. Bye.